Good day, I'm J Wildberger. In today's video, we are going to be looking at how the algebra of Boole simplifies circuit analysis. So this is a rather big topic. I'm going to try to reorient how electrical engineers are taught this entire subject of analyzing circuits via the mathematics of Boole or Boolean algebra. And the way we're going to proceed is to try to identify what are the main tasks that we, or electrical engineers, actually are interested in when they're doing circuit analysis. And then I'm going to try to move towards this claim that overall the algebra of Boole is a simpler and more powerful tool than Boolean algebra for circuit analysis. All right, so this is a very big and bold claim, which I'm going to try to demonstrate to you. And I appreciate that there's a lot of vested interest in the status quo educationally, the way we have it now, because it takes a lot of time to learn Boolean algebra and to become familiar with the various tricks and so on involved in that. And what I'm asking is that we put that aside and learn something new. But the advantage is that the new thing that we're learning is so much simpler and ultimately more powerful for most of the applications. That's what I have to try to convince you. Okay, so in a way, this is a little bit like my campaign to get people to rethink trigonometry. Okay, so with rational trigonometry, we have an alternative to classical trigonometry, which is also really dramatically simpler and more powerful. But the reality is that after you've spent several years learning all the little tricks and idiosyncrasies of classical trigonometry, you're not that eager to give it up and learn something new, even if that something new is, in fact, ultimately simpler and better. Okay, so yes, it does take some time, and I'm hoping that electrical engineers will be open-minded, because electrical engineers are practical people. They want to get the job done. They're not wedded to a particular ideology, and I think I can convince them that if we can perform calculations and we can build circuits in a faster, more pleasant, more easily understandable way, then hey, they'll move in that direction. So that's what we're going to try to do. So I want to start by going through some examples, very concrete examples, so we can get some experience understanding how the various manipulations are done, both in the Boolean algebra system and in this new, or somewhat new, algebra of Boole system. And a good place to start is with this particular network of gates. Relatively simple. We have three gates here. This is a NAND gate, this is an OR gate, this is an AND gate. We have two inputs, A and B. And let me just remind you how to read this. So we have currents coming in here potentially, either in A or in B. And this node here means that this wire and this wire are actually connected. So the signal from A is both going into this input of the NAND gate here and also to this input of the OR gate here. The crossing that you see here is not a connection. So these are just wires that one's on top of the other. So the current from B is going to this point, and there's a node here, so it's forking into this direction and this direction. Okay, so we could describe the effect of this gate, which is composed of these three individual sort of basic atomic logical gates, in the following way. So overall, the last one here is an AND. So this is a combination of this input and this input. So there's an AND here. Okay, now the top entry here is the result of this NAND gate, which takes inputs A and B. So over here we have A, NAND, B. That's representing what this gate does, giving the input here to the AND gate. And the other gate here, this OR gate, is taking again A and B, and it's outputting A or B. So that's the other input into this AND gate. So this is a way of describing the gate which doesn't involve choosing Boolean algebra or the algebra of Boole. It's just a logical explanation of what's happening at the level of the gates themselves. Okay, so now we want to apply algebra to this situation as as we know is a powerful thing. So in the Boolean algebra situation, what happens to this? Well, first of all, this AND is a product. So this is represented by the product of what's here and here. Okay, now what about here? A NAND B. That is A B bar. So it's the negation of the AND, which is represented by a product. AB represents the product, A and B, and then this bar over it is the negation of that, so that's AB with a NAND gate. And the A or B is represented just by our circle sum. So I remind you, in this laying out of things, the OR gate is represented by a circle sum, not a sum itself. Okay, so that's the way we represent this combination of gates in the Boolean algebra framework. In the algebra of Boole, what happens? Well, it's a little bit different. So it's still the basic same structure. We have an AND, which is still represented by a product. A NAND B is the inversion of A and B. A and B is just the product. So the product has the same role in both systems. But to invert the AND, we have to add 1. That's how we invert in the algebra of Boole. We add 1. So 1 plus AB, that is the algebra of Boole representation of A NAND B. And what about A or B? Well, the fundamental other operation is this addition, and that's an exclusive OR in the algebra of Boole. And to capture the inclusive OR, we have to use A plus B plus the product AB. Right? So this is how you interpret A or B in the algebra of Boole. And so we have to take that product there. And I'm just reminding you here that A plus B, that's A exclusive OR B. A circle sum B, that's A or B, like an inclusive OR. And AB is the product, that's A and B. Okay, so that's our conventions for what these symbols mean. All right, let's start our simplifying with the algebra of Boole. So here is again the expression that we're interested in simplifying. 1 plus AB times A plus B plus AB. And how do we simplify? Well, we just use ordinary polynomial arithmetic, otherwise known as algebra. This is the beauty of the algebra of Boole point of view. Okay? There's nothing special going on here. There's nothing that a high school student doesn't already know how to do. We're just expanding this thing using polynomial arithmetic or algebra. Okay, so what do we get? So 1 times this is A plus B plus AB. And then AB times this is ABA plus ABB plus ABAB. Okay, and now we use the commutative law to simplify these a little bit. There's an A plus B plus AB, and this is then A squared B, and this is A B squared, and this is A squared B squared. And now we use the crucial property that x squared equals x. That's one of Boole's main identities, which makes the algebra of Boole so powerful, that we can drop the powers of things. So this A squared is the same as A. This B squared is the same as B, and this is the same as AB. So this whole thing becomes A plus B plus AB plus AB plus AB plus AB. And now we use the other important identity of Boole, which is that x plus x equals 0. Whenever you have 2 of anything, it's the same as having 0 of that thing. Okay? 2 equals 0 in this bifield arithmetic. So this AB plus this AB is 0. This AB plus this AB is 0. Or another way of saying it, the sum here is 4AB, and 4 is also equal to 0 because it's 2 times 2, which is 2 times 0. So all of these cancel, and we just get A plus B, which we recognize as the standard XOR gate. That's the basic operation, one of the two basic operations in the algebra of Boole. So we've simplified our gate, and we've realized that it's effectively just the same as the XOR gate, represented like this. So that's how the derivation of the simplification of this little circuit works in the algebra of Boole. Okay, so now same analysis, but with Boolean algebra. Here is the expression of the original gate in the Boolean algebra story. So AB bar, that's the NAND, and A plus circle plus B, that's the OR, and the product is an AND. Okay, how do we simplify this using Boolean algebra? Well, we have to remember these various identities, that were laid out by Huntington, going back to, well, Peirce and Venn and De Morgan and others. In fact, the De Morgan law here is quite useful. So we can take the product AB bar and replace it with A bar circle plus B bar. Okay, so we have this sum times this sum. Okay, now we can use the distributive law because that's valid in this algebra. So we can replace this with A bar A plus A bar B plus B bar A plus B bar B. And all of these pluses are circle pluses. Now what happens? Well, this A bar A and this B bar B are both 0 because 1 times 0 is 0. And if you have 0 plus something, well, that's just the something. 0 just disappears. So this basically drops off, this basically drops off, and we just get the two middle terms, A bar B, circle plus B bar A. And that's a kind of simplified form. It's not possible to really simplify it further than that. So now we have to identify, well, what kind of operation is that? What kind of logical connective is that? Well, let's just go back to the truth table point of view. So here's A and B, the 4 possible values for that. Kim, can you just hold on to that for a little while? Okay. And here's A bar B, which is the inversion of this times this one. So there's only going to be a 1 when picked up there. And here's B bar A. So we take the inversion of this, 1's there, and multiply, and we get a single 1 there. And then when we take the circle sum, we're just taking the OR of these two. So we get 0, 1, 1, 0. And we recognize that this A bar B, circle plus B bar A, is in fact our standard XOR gate. So we arrive at the same conclusion as we did for the algebra of Boole analysis. But I want to point out that there's a little bit of a second possibility here. So when we were simplifying things, why is this kind of a nice end result? Well, because it's a sum of products. And that's kind of familiar to us. That's how we typically like to reduce sort of polynomial expressions. We get terms, and then we simplify the number of terms and write things like this. But in fact, if you look at this expression here, it's actually quite parallel to this one. And so we could possibly, I guess I have a red thing here. Let's have a look at this one. This here is also a candidate as an answer because actually it has the same kind of form. Instead of having a product here and a product here with a sum in between them, there's a sum here and a sum here with a product in between them. So in terms of numbers of operations, it's really the same. So this is also an answer. Instead of being a sum of products, this is a product of sums. But in the Boolean algebra situation, the sum and the product operation, the circle sum, the circle product, have a kind of dual relationship. Because the De Morgan's laws allow you to freely go from one to the other just by taking a bar. So with the bar, we can go from sums to products and vice versa. So there's a kind of a symmetry there. So it's really only a matter of preference whether we prefer this as the answer or whether we prefer this as the answer. Okay, so that's an important little ambiguity that's present in this Boolean algebra situation, which we did not see in the algebra of Boole. And that will play an important role as we develop things further. So I think this example illustrates a first main task that we can identify, something that we are going to want to be doing with logic gates. We want to reduce or simplify a given combination of gates to a canonical form. So we have some big combination with lots of ands and nands and ors and who knows what, and there might be dozens or maybe hundreds of different gates, maybe like dozens of inputs. It might be very complicated. And we want to be able to simplify this thing and say that it's effectively the same as this much smaller, more compact, easier to create system. Okay, so that is clearly a main kind of objective. And so to reinforce that and to give us a little bit more experience and also touch base with an important additional aspect of the previous example, let's have a look at this example now. Okay, so it's also a system involving two inputs, A and B. So it's still relatively elementary, only two inputs. But now all of the gates are NAND gates. Okay, so we have A sending a signal here and also here, and B sending a signal here and here. And this one here, whatever it is outputting, that output is going to both of these inputs of these NAND gates. And then the result of these two is put into this NAND gate. So we get an output C. We want to know what is this thing. Okay, so here is just a logic gate description of things. We haven't really introduced any algebra at this stage. So let's just see if this makes sense. So the large scale thing is that this is a NAND. It's a NAND between this big thing and this big thing. That's representing here, right? This is a NAND of this and this. Okay, so what is the top entry of this NAND? So it's the result that we get from this thing. What are we getting from this thing? We're getting A, but also NAND, because this is a NAND gate. What we're getting here. What are we getting here? Well, it's the result of this thing, which is an A NAND B. So what's entering here is A NAND B, and we're NANDing that with the A coming from here. That's a description of the top part of the input here. Okay, the bottom part, which is this NAND gate, is also a NAND, but now it's a NAND between this same output that we had here, which is A NAND B, that's coming in there, and this B coming in there, so NAND B. So that's a logic gate kind of description of what this combination of the gates does. So let's first simplify this with the algebra of Boole. And I have to remind you that A NAND B in the algebra of Boole world is 1 plus AB. So AB is the product and we add 1 to something that's inverting it. Okay, so here's again the thing that we have to simplify. So let's convert it first into the algebra of Boole. So what's in this this NAND here? This is the big NAND, okay? So the big NAND is 1 plus the product of this thing and this thing. So it's 1 plus, and then there's a bracket and a bracket. This bracket represents what's inside here. Let's check that. So what's inside here is an A NAND something else. So that's a 1 plus the product of A and this thing. And what is this? Well, that's A NAND B, which is 1 plus AB. So this bracket represents that combination. We're NANDing that with this one, and this one is represented by, so it's another NAND, so it's 1 plus the product of this and this. A NAND B, there's again 1 plus AB, and we multiply that by B. Okay, so now we expand. And fortunately, we only need to know how to do polynomial arithmetic, which we all know how to do because we learned that in high school. So we expand what's inside here. 1 plus a squared b. Here, 1 plus b plus ab squared. Okay, now we could go ahead and expand this, but the beauty of the Boole algebra story is that we always have at our disposal these two important reductions, that x plus x is always 0 and x squared is always x. It's always those two. So this a squared is the same as a, and this b squared is the same as b. So it makes sense for us to just simplify it at this stage here. We don't actually need to do that, so we could actually just expand this out and do the simplification at the end. But if you're doing this with pen and paper, it's probably more efficient to simplify as you go. Okay, so now we have 1 plus a plus ab times 1 plus b plus ab. So we have to expand this out. There's the 1. 1 times all of this is 1 plus b plus ab. A times all of this is a plus ab plus a squared b. And ab times all of this is ab plus ab squared plus, after we rearrange, a squared b squared. That ab times that ab is a squared b squared. Okay, so now what do we get? Well, now we have to remind ourselves that x plus x is 0. So whenever we have 2 of anything, it's gone. So this 1 plus 1 is 2, it's gone. We have a b and we have an a. There they are there. And otherwise we have an ab. And here's another ab. And what about this? Well, that's ab also, because that a squared is the same as a. So that's another ab. So we've got 3 of them so far. Here's another one, that's 4. Here's another one, that's 5. And this is actually another one, because a squared is a and b squared is b. So this is just another ab. So altogether we get 6ab. And 6 is the same as 0, because 2 is equal to 0. Right? So any even number is equal to 0. So that disappears and we just get a plus b, and we recognize that's the XOR gate again. So we're getting the same effective gate as we did in the first example, even though it's quite different. It looks quite different. It's got NAND gates and it's configured differently, but its logical effect is the same as the one that we started with, which is essentially just a simple XOR gate. In Boolean algebra, a NAND b is a b bar. Okay, so there's the expression that we're interested in, and we have to rewrite it in terms of Boolean algebra. So we'll concentrate on this NAND. This is a NAND, so it means that we have to take this big thing and multiply it by this big thing and then take a bar over it. Okay, so what is this thing here? This is an a NAND b. Okay, so that's a NAND, so it's the product of this a with this thing. This is a b bar, and we have to take the bar of that because that's how you do a NAND. You take the product and then you put a bar over it. So this little bar here is the bar over this first product. Okay, that was that one. And then this thing here is a NAND b, so it's another NAND. So we have to take the product of this thing, which is a b bar there, with b, and we have to take a bar of all of that. That's that thing there. Okay, so this big NAND here is the product of this, which is that thing there, including that small bar, that medium bar, and times this thing, which is this thing here, including that bigger bar. And then we have to bar the whole thing. So there's a big bar that goes over the whole product. So there's kind of 3 levels of bars floating around. Okay, so that looks a bit intimidating, but if we remember De Morgan's law and this sort of involution that x bar bar equals x, then we can simplify it pretty easily. So how do we do that? Well, first of all, this is a bar of a product. Okay, so it's like a times b bar. So De Morgan tells us that that's the same as a bar circle plus b bar. So we're going to take just this ingredient and take its bar. And we're going to circle sum this ingredient and its bar. But if you take the bar of what's involved here, including this bar, then you can use this. The bar of the bar is just the original. So this is just the same as A times AB bar. And similarly here, when we take what's involved here, including that bar, and we take its bar, then the two bars on top of each other, they cancel, and we just get AB bar times B. Okay, so now we can simplify again using De Morgan, because it's AB bar. We could write that as A bar plus B bar, circle plus B bar. And then there's a plus. This one here is A bar, circle plus B bar, still multiplied by B. And now the distributive law here, A times A bar plus A B bar. That's all on the left-hand side. And then over here, A bar B, circle plus B bar B. And we're taking a plus of all of those. Okay, so now there's just pluses. So now the brackets don't matter. And we remember that A times A bar is going to be 0. And B times B bar is going to be 0. So the effect of this and this is going to be 0 because we're adding 0 to something. So that's going to just disappear. And we're just going to get A B bar, circle plus A bar B. And we recognize that's essentially the same thing as the XOR expression that we got previously. So again, we verify that this combination of 4 NAND gates is doing the same job as the XOR gate. So we're touching base here now with an interesting discovery that was made by electrical engineers, namely that these two gates, the NAND gate and the NOR gate, so this is an AND gate with the inverter, and this is an OR gate with an inverter. These are both universal gates in the sense that if you only had NAND gates, you had a big bucket and only had NAND gates, you could still do all of this analysis because each of the other gates can be created by suitably clever combinations of NAND gates. And the same is true for the NOR gates. All gates can be made just with NOR gates. So if you had a big bucket of NOR gates, you could also just use them in order to reconfigure any other gates appearing as combinations of NOR gates. It's a pleasant exercise to demonstrate this. And if you're an electrical engineering student, probably you end up being tasked with doing something like this to demonstrate that the other gates can be made from just NAND gates and just from NOR gates. Okay, so we've made some initial contact now with an important problem. The problem is, how do we reduce or simplify a complicated circuit to get a canonical form? And we've seen that the kinds of things that we're doing and the kinds of things that we get are a little bit different in the Algebra of Boole story and the Boolean algebra story. And that will become even more pronounced when we move from 2 variable systems to systems with more than 2 variables. So we're going to have a look at, what are the kinds of canonical forms that a circuit can end up being reduced to in both of the systems. And so we're going to be moving towards seeing more and more clearly as we go along that the algebra of Boole is really more powerful and sort of conceptually just a lot simpler than the Boolean algebra. So that's very exciting. I hope you're going to join me for that. I'm J Wildberger. Thanks for listening.